Alrighty, it's 3:40 on my side. So one more thing we'll just take a look at on this 2D grid before we move on is some of the visual options on it. Pick one of the cells there, or pick the grid from the object tree and see that guy highlighted again. So just quickly, we already kind of took a little look through, comparing these primary values to the interpolated values. But for now, I'll go ahead and turn them off. And turning them off actually shows some of those cells where we are actually seeing some influence from those lower primary values that were hidden by showing the points themselves. But a couple options we do have for 2D grids are deforming this surface by some data. Do something like that just to make the appearance a bit more drastic. Blending data between two types. So right now I've already got this painted by copper, but I could throw lead on here as well. Say, oof, we got to fix that color scale too. There we go. And now we can scroll back and forth between lead and copper assays. And then there's hill shading. I'm not going to show that one because it doesn't really look great with this data. But if you wanted something from here to take away, bring into another platform, your GIS, plot onto a report, you can draw some contour levels on here too. So the preview here comes in yellow, but I can just as easily change this to black and actually create an object from that showing the contour level. Then you could take this guy and export this to DXF shapefile CSV. Since we're not really going to touch 2D grids again, those are your options there. But for now, I'll delete those contours. Don't need the grid. I'll just turn it off for the time being. What we'll do now is take a look at our field measurements. So just quickly, let's check that the elevation is correct, and it appears to be. Well, we can double check that just by turning on the topography and doing a quick rotation there. Everything should plot on the topography. And then we'll expand the field measurements object to view the properties on it. And recalling from when we imported it, we had an azimuth and dip. These were automatically grouped when we imported them into an azimuth, dip, strike, and dip data group. These orientation data groups are handled a bit differently than other pieces of data because we can use them to draw orientations on our objects. We can visualize these as 3D vectors shown with arrows, or as a plane, as a tablet. The key part there, though, is that you do need to make sure these are grouped. In this case, it happened automatically, but if for whatever reason it didn't, you can right-click and go group data. Make sure that you're picking the right dip direction or strike and dip group, and grab those guys, move them over, and then just make sure that strike is mapped to strike and dip is mapped to dip, or whatever, however you've got this orientated. If you wanted to do a 3D vector, we could do something like this. You might want to do this with your polymetal assays, polymetallic assays with your copper, lead, zinc, and then draw that association as a 3D vector. Or you might see it with a magnetic vector model. Just so you know it's there, we're not going to do anything more with that because in this case it happened on import. So with these field measurements picked, what we'll do to kind of help our visualization of them is make them a bit bigger. Select the orientation. I've got the object selected. I'm picking orientation. And then in data group, the only option for us there is going to be our azimuth dip orientation group. And then change that symbol, though, to tablet. So these are probably still going to be pretty small. So we'll just start by turning the length up to something like 350. And now you can see those contact orientations plotted as tablets. Only other thing to do might be to paint by unit. Now we've got a bunch of funny colored tablets that don't associate with our units. So we can quickly recolor those. The same kind of way I hinted at earlier by clicking on the color and screen picking from the map. So we've really quickly talked about the hidden formation and the mill rock member, but this Mississippi is meant to be the light blue color on the right hand side. No. Yep, that's it. Is the light blue color on the right hand side, and the Lewis formation there is the slightly darker blue also on the right hand side. We don't have a color for this F1. This is this fault that traces right through the mill rock unit. So we'll take this F1 and color it. I don't know, you can pick yourself. I'm gonna make mine gray, but you've got full creative freedom over what you want to color your fault points. Okay. What we're going to do with these tablets is use them to project these contacts down at depth, build a projected contact trace at depth, and then digitize a surface to represent our contacts and our F1 fault. Well, we'll start with the F1 fault and see how that goes. There are backup surfaces to bring in because we probably won't want to fiddle fuss around all the contact surfaces here. Basically, the idea here is that, starting from before we have drilling, to come up with a drill target, we need something to point the drill at. And usually the first thing we can put together is a surface projection based on our mapping or based on structural measurements. So if we're lucky, we might have a geophysical model and we can target a geophysical region. But for the sake of this one, we'll just build a surface, and then we'll build a set of surfaces and then bring in some drill holes to test those surfaces. Right, so for digitizing, let's turn off those field measurements for a moment. View from top again. I've been doing a bit of rotating. And what we'll want to do to digitize something like a surface trace on that fault is, and I'm going to bring up that controls menu and scroll down to the bottom of it, O and left click to create a curve. So this will create a polyline string curve trace. So, and the one we want to digitize, you can follow along with me if you like. It's marked as a thrust fault here, but then it turns into kind of a projected dashed line trace coming up through this area. Keep in mind, as we digitize this line, it is going to be snapped onto that topography. The snapping always happens on whatever is whatever's closest to the camera. The snapping is going to happen regardless. There's no way to turn it off. What will change if you click this magnet button for your snapping is that you'll be snapping to the nodes on an object instead of just to somewhere on the triangle. There's a picture in the user guide that can explain it a lot better than I can verbally. So if we want to look at that in more detail, I can pull up that picture. But for now, you can test it for yourself. If you want to snap specifically to a drill hole interval, you'll want to turn this on. If it's not on, you'll snap anywheres along the drill hole trace. So let's start digitizing. Press O and start left clicking. And just click, click, click to draw your, there we go. We can kind of guess how that fault connects with this contact here, but we'll just leave it here, right where that red body kind of pinches off in the middle. If you misplace a node and you would like to move it, press and hold D and left click and drag to move that node around. You don't need to restrict that just to the one either. If I want to move several, I can shift click and multi-select this whole section. See that I've got a multi-selection in the data table, and I can press D and drag that whole selection. If I've placed too many nodes, I can collapse some of them. So here, I'll turn off the topography so it's a bit easier to see the line I've drawn. I can take these two and shift delete, which collapses them. It removes the node, but leaves the line itself intact. If I want to bring them back, I can B and left click somewhere on that line to insert nodes on that line. Let's see what else. Control delete will delete the nodes and break the line. And something to keep in mind, particularly when editing objects or digitizing, is your selection levels. So one point of frustration, why can't I select my nodes? My selection level here is at the object level and not at the node level. Here, if I'm pressing D and trying to drag this around, my only choice is to grab the whole object. Now I need to fix that and put it in the right place again. Oof. Oh yeah, that's the problem. There we go. Somewhere just about there. You can also set to segment selection and move segments around. That functions just in the same way as selecting two nodes and moving them around. Take a couple minutes to play around with digitizing some lines, moving them around. When you're done, you may notice as you've been editing your object, got this edit curve text shown here. That's indicating that we are in editing mode. To exit that and stop editing, press escape. We prompted to change this, and we can call this F1 surface because we're digitizing this trace on surface. We've snapped it to topography and put it on the surface. And we want to differentiate it from the trace that we're going to project to depth. Okay. Now we've got that curve appearing in our object tree. Any questions on playing with lines and line digitizing? We're not actually going to do a whole lot of this. And really the main goal here anyway is to build a surface. Because at this point, we're going to start working in 3D. We've spent long enough on the 2D grids, and it's time to start expanding vertically. All right. So what we're going to want to do is turn on those field measurements again. Let's pick unit, go to your data colors, and we're just going to approach these one at a time. So let's just start with that F1 fault surface. So pick that F1 and isolate that to ignore all the other structural tablets. Usually when working with digitizing or surface editing, the fewer things we can put on our screen, the better. Too many things just becomes cluttering. They get in the way, and you can unintentionally snap to things that you don't really want to be snapping to. So we'll just look at the tablets for that F1 surface, and we should have two of them, here and here. Now, let's say we want to project this surface somewhere down to 2 kilometers subsurface. And we've already checked, let's assume that we've already checked and validated our structural measurements here. They're not just small scale measurements. They should reflect the structure kind of as an overall whole. That's one thing that tends to get a little lost in translation, going from the field to interpreting larger scale structures is small scale variations in your orientations. So if you find yourself with a great deal of structural measurements thrown at you, just like working with point interpolation, we're going to want to find an average and build out a rough idea rather than focusing too much on the small level detail. It's kind of keeping that understanding of what scale we're working with and what level of resolution in our data is appropriate. So in this case, we're assuming that we've got two measurements. or two structural orientations that represent the feature here as an overall whole. And what we can do to set up that projection is, I guess we'll unlink here, leave the width at about 100, and turn this length up to like 5,000. And we'll see them do something like that. Because ultimately what we want to do is make a copy of this line and drop it right down to somewhere on this level. To keep ourselves somewhat organized, we can set up two horizontal slices, one at our projected depth and one at surface. So we'll go back to, if you haven't closed it, you can reopen a map viewport or just a regular viewport, either or. Now for me, these are tabs. I can take my viewport 2 and tile it on my visual parameters again, something sort of like this. And then in the first one here with my topography turned on, I'll click the look north button. Now I can see that those two tablets extending like way up into the sky, but also way off to depth. And make sure you're working in parallel view. So check that button there, because if we start projecting things and we're in projected view, it's not true. Like we're not looking along the same plane in projected view, right? Because everything we see is converging to a single point somewhere ahead of the camera. So looking north, we can see our topography surface here. We'll cut a slice on it by pressing X and drawing that line. That'll chop off part of that tablet, but here really I just want to look down on this. Pick that slicer, change it to a thickness slice and give it, a fair bit just to make sure we don't get part of our topography chopped off. So what I did there is I picked a slicer. That's a horizontal plane slicer at surface, and checked on slice mode and put the thickness to 150. Okay. Then in viewport 2, we'll do something similar. Make sure that your view is set in parallel again. Look north. Here in this one, I do want to turn off that quick slicer because the plane I want to draw is down here. And I'll press X. Do the same thing, drawing a horizontal plane somewhere down at depth there, and then look down on it. Oh. So what I just did was I re-registered my original slicer because I didn't shift X and click. To create a new slicer, shift X. Good to know. So we'll just recreate that first one. Shift X, click and drag here. Now I've got a quick slicer and a slicer 2. So I want my slicer 2 at surface level to be active in my primary viewport. And I want my slicer 2 at depth to be active in my viewport 2. So now I can see, and I need to fix up the visual parameters again for that first slicer, and also for the second slicer. That's already set to 150, perfect. Okay, so they should both be set to slice and about 150. There we go. And you should see just your tablets there. Might be easier here if I actually change that color to white, just so it shows up a bit better on the gray background. I've got those two projections of the orientation measurements at surface projected down. And what I'll want to do with that surface trace we made is make a copy of it and just drop it right down. And then from there, we can adjust it to make it fit where those tablets are projected to. So we'll take F1 surface. We can copy and paste these objects in the object tree. I kind of did that by accident earlier with those outcrop geochem points. With Control C and Control V, Now I've got a second F1 surface. These are exactly the same in the same location. I'll take this second one and rename that projected to keep them differentiated. Make sense so far? What we'll do next is right click on that F1 projected, go translate, rotate, scale objects, and leave everything here empty. Just go down to this translation section and put 2000, minus 2000, sorry, minus 2000 to translate it negative 2 kilometers down. And then click OK. I think that I should have done that maybe first before setting up that slicer. Didn't quite make it. That's okay. We can recut that slicer by looking at it and cutting the slicer on that line. The thing we need to adjust here though, just shift X and then do this again, drawing that over top of how far I projected that, that line, and then double check that we're working with a thickness type slice, and also that it is not turned on in my primary viewport. Okay, now we should see something like this, where we've got in our primary viewport, the surface, the map, the trace we've digitized, and a copy of that projected some, directly down 2000 meters. So we'll grab that projected, F1 projected, find the edit button in the right click menu. And what we could do here is just switch to object level, grab that whole object and just shuffle it over until it meets approximately where those projected tablets are, and then go, node by node and try to match it a bit more precisely. It doesn't need to be perfect, and we actually might benefit here from simplifying the geometry a bit by collapsing some of these segments by shift selecting them and then shift deleting. Because in reality, it's not likely that we have the same geometry 2000 meters below. We just want a rough idea of where this thing is so we can test it with the drill hole. And that is what I've come up with. If we're feeling good, we'll tie this back together and start building a surface from it. Okay. So now that we've projected that down, we don't really need the second viewport anymore. We're going to work with this just in 3 dimensions and rotate around. So you can hide that second viewport if you wish. Turn off all your slicers. We'll turn off the topography too. We don't need it. And at this point, we don't need those tablets anymore, so we can turn those off. But basically here, we've got those 2 lines. We can kind of like see roughly what the surface would look like if we just stitch these together. But to actually stitch them together, we need to finish the outline and place a couple control points in the middle, just to constrain how that surface is constructed. So part of the issue here is that we actually have these as 2 separate objects. That's okay. We can actually multi-select them, grab them both, right click, go to the create menu and go to create curve from lines. And we'll just call this F1 and boundary because we're going to use this as like the outside boundary of the surface that we're constructing. Okay, now we can actually turn these 2 off. Actually, you know what, to keep this a little bit more organized, I'm going to create a new group. Call this F1 surface modeling. And I'm going to place this projected and surface curve that I'm no longer using inside that container just to get them out of the way. It's kind of the way I like to approach object editing and working with different objects is I'll leave the one that I'm working with at the workspace level. And as I finish with other ones, I'll place them in a container group just to declutter, make sure I'm not editing the wrong object. It happens a lot. You'll have multiple sets of lines, especially as you get into, we're not doing it in this exercise, but walking through drill holes and drawing your interpretation picks on sections and building surfaces out of those. In this case here, we're just projecting something down from surface, but a more involved workflow here would be updating this by drawing a bunch of ribs along a contact using drill holes. Anyways, back to this F1 boundary. Let's go back in and edit this. There's a couple line construction tools I haven't talked about. That's joining and closing. So we've got different icons here to indicate whether this is an open curve, it's not connected in a loop, or it's closed. I'm going to close this guy by making sure this is at the node level, pressing J, clicking on one node and then the next one. That joins the two. And again, now my icon here is changed to show that this is a closed curve. It's completely wrapped in a loop. That is important because there are some things, like particularly with respect to surface construction, that you do need closed curves to do. You cannot do them with open curves. I'm going to press escape. Then we'll digitize a new curve just to fill in the inside here. We need a little something else to give for control points to the surface designer tool. So what I'm going to do is actually turn on that snapping because I want to snap to my nodes. Press O to start digitizing again. Actually, just to make this a bit clearer to see, let's turn up the node size. There we go. I'll press O. I'm not in editing mode right now. If you are in editing mode on your F1 boundary curve, press escape to get out of there. And then press O to start snapping some lines just kind of like that to like lace up the insides. Doesn't need to be overly dense. It's actually probably better the less dense it is. We're just doing something rough. Then once you're done with that, press escape. Call this something like F1 internal. Now the restriction there on the surface designer is that it is actually looking for nodes. It's not looking for line segments. So we need to like break up all the portions in here to get some points. That can be done with one of our right-click menu tools. So we'll right-click on that F1 internal curve that we created, go to create, and go to densified curve. And you can put the, what was it? Max segment length. Yeah, you can set this by curve, F1 internal, method, max segment length, and set that to 500. We don't have any properties to carry over. All we're doing is placing some nodes every 500 meters along this line. Click OK. That just gives us something like that right in the middle. And then at this point, we can actually get rid of that original F1 internal by right-clicking on it, deleting it, and rename this densified curve, our F1 internal, to get rid of all that extra verbiage there at the end of it. Okay, so now it's starting to look more like a surface, right? One more thing to do before we open up the surface designer is delete co-located points. So take your F1 internal, edit that guy, go to the node level, shift to multi-select, covering a box kind of like this. This is going to delete those nodes that we snapped when first digitizing this curve. The problem with them is that they're co-located with those boundary nodes, and they're going to give the surface designer some issues. It's going to say your nodes are too closely located. I can't build a surface here. So draw one like that on the top, and you'll see them highlighted in yellow. They're snapped right in the same place as those other ones. Then just go Control Delete. It'll break the lines. That's okay. Repeat at the bottom. Control Delete. When you're done, you should have something like that. Close enough? Doesn't have to be exactly the same. All right, and if we're there, let's go Utilities. Find the surface designer. Take a quick look that everything kind of lines up. The perimeter curve is where we're looking for that boundary curve that we stitched to, that we digitize on the surface, project it to depth, and then stitch the ends together. Perimeter curve. And the control points are going to be that internal curve. Called points, we can use curves for these too. It's just going to look at the nodes. That's what to be aware of there. We'll call this surface F1. And try clicking create surface and see if you find this triangulation failed error. The reason this comes up is because the triangle size is suggested based on the size of your boundary curve and not on the spacing of the control points. So like 9 times out of 10, the solution there is just reducing triangle size. Try reducing that to about 40 and seeing if that generates a surface for you. The other time, it's because you actually do have a co-located point. That's the same error you'll see if you've got co-located points. Could be snapping to your boundary points or snapping within your internal control points. Something fun we can do here is tick on auto update and start editing either the boundary or some of our internal points. So let's say maybe I'm not really happy with the dip on this fault. I can tick on, oh, it's kind of hard to see that there, tick on auto update, multi-select all those points at the bottom and drag them all over here. And try to redraw the surface like that. You can do that with the internal points as well. Though it doesn't have to just be moving. I could delete these. I could delete that whole bottom and see how it looks. Let's see. Oh, I can't do that because that was the boundary. Yeah, that's gonna fry it. Okay, we'll put it back. Control Z does work on editing objects in case you do something reckless like that. But I don't. The thing to keep in mind, see how it kind of tries to roll to the left before coming back to the right. What we're doing with the surface designer is actually interpolating where that surface should be based on the control points. It's smooth. It doesn't necessarily fit those control points exactly. It's not a strict like Delaunay triangulation. It does do some smoothing. So take a look at what you've got and make sure that it's close enough to your controls that you find it acceptable. And if you do see something like this, usually the solution there is moving that guy back like that to kind of flatten that plane out. So we've kind of captured the little rolls we had at the top, the kind of loose open folding. And we've kind of smoothed out at the bottom a bit by simplifying the geometry. So I could take these guys and move them back in a bit here too. Generally, I don't really want to make a really aggressively undulating surface, especially if I don't know what's going on down there. That's all part of the discovery method. So done with the surface designer, we'll close that. And the idea here would that you could go ahead and continue on with the other those other units you have in the map. I'll give you that one you can do on your own time or as homework if you're interested in playing around the surface designer. But for the time being here, I did include under exercise 13 a surface modeling GeoH5. Just go ahead and bring that one in. This time, instead of clicking, don't click open and replace workplace. Just click import, and that brings a few surfaces in, a few rough surfaces in that have already been done. You do get a copy of an F1 surface in here, essentially the same as the way I just did it. In case you want to pick this back up without building that surface again. So for me, since mine are pretty much the same, I'm just going to turn off my F1 bits and pieces and put them inside that F1 surface modeling container group. And I'll bring this surface modeling one out to workspace level and get rid of that. Yeah, and so essentially after importing that, you should have something that looks like this. We've got mill rock base contact, hidden formation base contact, and that F1 surface. Okay, how are we doing? We've got about an hour and 15 left. I think we're still doing pretty well here. Yeah, we're doing pretty good. Okay. The next thing that we would want to do, you know, assuming we were constructing this from some real field data, is test how these surfaces actually compare to real drill hole data. And we have some drill hole data, so we'll go ahead with the next step and bring it in. The idea there would be, stepping away from the known into the unknown. Aha, one other thing I wanted to touch on before bringing in the drill holes is, given that we're actually interpolating, well, we're projecting and then interpolating between our projection, where do we feel most confident about the spatial location of these surfaces? Do the projected lines have the same confidence level as the surface lines? Do the in-between lines, like the internal lines, where do those kind of sit in your understanding of how confident we can be in the spatial location of these surfaces and contacts? It's a fairly simple extension of a feature observed at surface, but in reality, like, we don't have any information about what's down here. So we're really just doing some guesswork, and then we got to test our guesswork by collecting some real data down there. Every new piece of data helps to reduce the uncertainty, but we can never completely eliminate it. You can't see everything. Drill holes, yeah, that's where we want it to go. So to help kind of point that out, let's bring in some drill holes and see how our surfaces actually stack up. Drill holes are one of the few objects that cannot be imported by dragging and dropping. So for that one, we do need to go to the File, Import, ASCII, and Drill Holes menu. So find that one and open up the drill hole importer by clicking on drill holes. Here, we're prompted to pick collar, survey, interval, and point log files. For now, let's pick the browse button beside collar and look inside data, exercise 14. Yeah, exercise 14, and pick that collar, flimflom DDH collar.csv. And then survey. This should bring you to the same location in exercise 14, pick survey. And we'll pick in that one geology interval file. That should be in the interval log file and not point log. Difference there being that interval logs are from to and point logs are depth, point depth. And we'll click OK, and we'll see a new window open up. Much like the ASCII importer we used earlier to bring in the points, we've got some expected fields in the top. We need drill hole IDs. For our collar table, we need XYZ coordinates. We need lengths. We don't need azimuth and dip, but we either need azimuth and dip in the collar table, or we need a survey table that has azimuths and dip. We need something to give the drill hole an orientation. If you've got planned holes, you don't need a survey file, but you would need to put the azimuth and dip in the collar file in that case. And then generally, we're not going to see much else in our collar file. The status there is just a way that we can differentiate between like planned, in progress, completed drill holes. We're not going to use that for these. And then that message there we're seeing in the all fields section is just that the azimuth and dip columns in this case are actually not filled out because we've got a survey file that we're going to use instead. And then you get your little preview of a list of drill hole IDs, collar coordinates. Total length, we do need to plot the drill hole because the path is plotted based on this collar table. So it won't import correctly if you don't have a total length, even if you have completed interval tables elsewhere to import. We'll click OK, then we can move on to the survey file. This also fairly straightforward. Drill hole ID, depth, azimuth, and dip. It's a special kind of point log file. And then the geology menu, the geology table. So interval logs will import like this. There are 3 required fields: drill hole ID, from, and to, and anything else is just extra. So in this case, we've got a unit classification. Very, very, very simplified geology corresponding with those surfaces we modeled. So we'll click OK. And that brings in those drill holes. They're really hard to see on my screen because they're gray on gray, so we'll change the color to white. Still doesn't really help. Maybe brighten up my background a bit and change the color here to more like dark gray. Okay. So these ones, just similar structure to the drill holes we looked at way back at the beginning of this. But we've only brought in the one table, just the geology table. So what we're going to want to do is check how our geology logs compare to those surfaces and see just how close to reality that is. So tick on the unit, turn up the log radius, and we don't really need air. You can color air whatever color you want, or just turn it off. And then set your color mappings there. You can use screen pick to pick the color of those surfaces. Mill rock should be yellow. Hidden should be green. And Blue Lagoon should be blue. You can pick this one if you don't have something to set it on. And so just quickly in 3D, take a quick look at how closely those surfaces respect the drill holes, and what do we think are actually happening at subsurface. Now, how do we fix this? Should the drill holes wrong or the surface is wrong?
Maybe there is a fault.
Could be part of the fault. How would we, so in that case though, we'll want to update the contact surface to reflect how it's being changed by the fault. Right? Like keep in mind here, we projected that surface down from a known data point, but what's going on between, in between where we projected it to and that surface, we don't know. So that's what we're testing with the drill holes, is what's happening here. Is our understanding of the geometry correct, or do we need to make an adjustment? And we can actually make an adjustment here fairly quickly to the surface. Like even in this case, in this case here, there could be faulting, could be a faulted offset, could be folding or rolling, just some irregular geometry we don't anticipate. This is a real situation at small scales, large scales, everywhere. When we go from a more limited or restricted understanding to kind of stepping out and building a denser or more fulfilled picture of what things look like. Right. So the next thing we'll do is update those surfaces to match the drilling. And we can do that fairly easily by grabbing some points from those drill hole intervals. What we'll do here is right click on our drill hole group, find create and desurvey drill holes. This is going to give us a set of points associated with our interval table. So we've got a from to log. We can pick locations in the middle, tops, or bottoms. Since we modeled these surfaces at the bottoms of the units, we'll take the bottom. We'll want to check that our master log here is the geology or unit. And we can give it a name, something like unit desurveyed. Did I go through that too fast? That desurvey menu, you can find that. Right click on the drill hole group, create and desurvey. Okay, and then you should, if you clicked on the drill hole group, you should have all the drill holes pre-selected. Take a quick check that you do, because we'll want points from all the drill holes. And make sure that it's set to the bottom. Master log is unit, and name it what you want. But this kind of makes sense to me, that I know what I'm desurveying by. Then we'll hit OK. And that point set that gets created there comes in at the base of all the units. What we'll do is actually replace the kind of internal lace work that we use just to fill in the center of the surface with these actual drill hole picks. First, though, we need to make sure that we're just working with the appropriate unit. So we'll update. What we'll do here is update the yellow mill rock surface. So just to help us, like I kind of mentioned, really helps to remove things we don't need. So let's turn off the green and gray F1 and hit information surfaces. We can turn off the drill holes too. We don't need the traces anymore. I'll turn up the sizes of my points just so they're easier to see, something like 8. So now I can see I've kind of got this field of points. Yellow on yellow is a bit tough. Probably a bit easier here if I show a white mesh on top of it. Now I can see that I've got this field of yellow points. I want to match these two. So the first thing to check is that I'm only working with the yellow points. If I just take this whole point set and try to pass that into the surface designer, it's going to grab the blue points, the green points, this white point too, and I don't want that. So what we'll do is pick unit, grab our Millrock member group from the data colors panel, and isolate it by clicking that one eye just on the right-hand side to show only selected. Just look at the yellow ones. We still need to use a masking property to split this off. It's slightly different than what we did with masking properties earlier, but the same idea. So I've set a visual filter and I want to record it by creating a masking property. I found that in the same menu, just right click on unit desurveyed, create masking property. Creation method here is visible association, right? Because we filtered off all the points we don't want. And we'll call this Millrock points. Okay, that gives us that masking property. Then from here, we can go create again and create object from masking data. So that's going to take those 8 points we identified with the masking property and create a second point set just subsetting the original one. Object from masking data is Millrock points. Okay. Now, if I've got this, it creates as a using the same name, but incrementing it by 1. Now, if I look at this and I look at the object level in the data panel, I can see number of nodes 8, which should match that 8 count on the masking property, which should also match the 8 count on our 6 Millrock visual filter. So just for clarity here, we'll rename this guy Millrock points. There's something else wrong with these points that we do need to fix. Any ideas? Not, that's okay. You'll need to turn on the drill holes to see it. So let's see, looking on my screen, these 2 points, would it be right to use these? So we need to grab those points that are actually at the end of the hole and delete them. So we'll take our Millrock points, we'll edit. We can pick these, Control and Shift. So what I'll do, I've got 1 point selected. I'm pressing Control and Shift at the same time and drawing a selection box around these 2. Now I've got the 3 selected. So Control Shift will add to your selection and draw a selection box. And we should have 4 of them that we want to remove. Once you've got all those selected, Control and Delete. Oh, confusion here is that I've selected the unit desurveyed points and not the other ones, and or all of them really. And do as I say, not as I do, and turn off the stuff when you're done with it so you don't pick the wrong thing. So the thing there that happens, at least to me, kind of often, is when I leave a set of, I do this, leave the first set of points on, I'll be selecting something and trying to delete it and hitting delete, and it's not deleting. It's usually because I've got that old one still on that I'm not editing. So making sure that we're just deleting from that Millrock points set that we created. And now we'll go escape. And now with the drill holes turned off, checking Millrock. Oh, I didn't have them selected at all, did I? I gotta go do this again because I missed them because I had the original units desurveyed selected. wrong selection level. Grab these ones, grab this one, and grab this one. Then Control Delete. And double check that when you tab over to your object level selection, you've only got 4 nodes selected. So there should be 4 of these points when you're done removing the ones at the toe of the hole. Okay, with that point editing done, turn off the drill holes. Those points are super hard to see. We'll make them bigger, make them darker. And basically the idea here is that we can go back into the Surface Designer, check off auto update. I'm going to rename this one F1 new. Could be F1 updated. And I'll take off that internal curve that we used the first time and instead take the Millrock points to use for control points. That's just going to take those 4 points to use on the inside. So let's try creating a surface like that. It's probably not going to look too... Oh. Got to tick for the Millrock. We've got to make sure we're picking the Millrock boundary and not the F1 boundary, Millrock boundary. There we go. So we can see how it's changed by kind of rolling out in this way. You can see even better if we cut a slice on it right through the center. You might notice that I just cut a slice and it did not apply to that surface. That is because we need to apply the slicer to the surface and also to this surface and potentially to the points as well, but I think that'll be all right. Got it from the other side, other side, there we go. Okay, so this isn't really how I'd leave this. Basically, that bottom projection is really affecting the shape of the surface and introducing this like near vertical roll. That isn't how I would expect that to continue. I have a known point here. We have known points where the drill holes intercepted the surface. What we'll want to do is continue kind of in that same projection and bring those bottom projected lines over to the right a bit. So I jumped a little bit ahead on this before playing with that auto update. But that's we'll use that auto update to change the bottom projection too. So I'll grab that Millrock boundary. That one was in since we didn't go through digitizing all these surfaces, that Millrock boundary was in that folder that was imported, by the way. So that is here. Turn it on. And start editing it. We'll add auto update. This should be Millrock new, not F1 new. And we'll start by just selecting this area at the bottom and dragging it over this way. Add this one here, just this one alone to straighten that out. And we'll keep doing that to try to straighten out how the surface is projecting down dip. And what we'll do to help this out a bit is actually turn that slicer off and then turn that surface off. So a couple ways to go about this. We can kind of rough something in 3D, but in practice, you'll probably want to take a more methodical approach to editing this, walking through in sections, right? Might be more intuitive to rotate things around and drag them around and move them, but it's a bit more rigorous to do it through sections. I'm not going to go through that setup again. We kind of covered that walking through with the model. So for now, just kind of drag that surface over until you get something that looks, not too excessively folding. We're not trying to model any really severe folds here. We're just trying to project these units down. If we see evidence of folding, then we should probably work it into our model, but we haven't seen that yet. We're just finding those pierce points and updating where the surface location to match those pierce points. Once you're satisfied with that, close off the surface designer and say, hey, I made a projected surface and then I updated it with some new information I collected. That's pretty neat. So just to catch ourselves up here too, because some of those other surfaces didn't quite match either, the hidden formation didn't. Instead of modeling the surfaces again, go over to the exercise 15 folder and grab surfaces remodeled and bring those in.